This video we are going to talk about different ways to combine two functions. We're going to start out assuming f and g are two functions that have overlapping domains. They're defined in x. They have some things in common. If I want to add them, noted by f plus g in parentheses, I take the two functions and I simply add them. If I would like to subtract them, again noted by f minus g in parentheses, I take the two functions and I simply subtract them. If I'd like to multiply two functions, noted with a dot for multiplication, I take the two functions individually and I multiply them together. Now, this may require some foiling, this may require the distributive property, different things that come into play with multiplication. If I want to divide two functions, noted by this fraction bar, I take the functions individually and I write them, one is the numerator, one is the denominator. But you'll note that it has one extra thing here that says g of x can't be 0. Because we're dealing with functions and we've got a fraction, we need to make sure that the bottom of this fraction doesn't turn out to be 0. So if there's anything in g of x that causes that 0, we have to take that out in our domain. These first four are very straightforward. They're exactly what you would expect. There is another one, a new one for a lot of us, that's named composition. It looks a lot like multiplication, but notice this is an open circle, not a dot, and it kind of looks like the word fog. That O means compose. Just like a dot means multiply, the fraction bar means divide, O means compose. So this is saying f composed with g using the variable x. And so we're going to do something like this, f of g of x. Now, one thing to note about this, the domain is all the x's in g, so that g of x is in the domain of f. What this roughly means is everything that's defined for x in my original function, g of x, also gets defined in the domain of f. And I'll go through in one example to show you these different things. So if I want to add these two functions, if I want to sum them up, I take x squared and I add x minus 3, and now I have a sum of two functions. Not as easy with difference. Here's the catch. I'm going to put this in parentheses so you kind of see them as two separate functions, but it doesn't change what my answer is. But now that I'm subtracting, those extra parentheses become a little more important because I have x squared, I have minus x, but I also have minus a minus, so I have a plus 3. I would highly recommend putting these in parentheses, especially when you're dealing with subtraction. For product, we're going to multiply these two things, so I'm going to take x squared, and I'm going to multiply it by x minus 3. I end up using my distributive property, and I get something like this. For dividing, I take them as they are. Remember, this fraction bar is kind of like a set of parentheses, but since I have a fraction, I have to remove 3 from my domain so I don't end up with a 0 on the bottom. Now for the new one, this composition, I'm going to actually start with function f, and function f says we're dealing with x squared. So I have x squared. But I'm going to replace x in that function with the other function. So now I'm going to take g of x and plug it in everywhere I see an x. So I replaced my x with the other function. I have composed f and g. Now, I should probably simplify this, so it requires me to do a little bit of foiling, but there they are, composed. Not the same answer I would get if they composed them the other way. Subtraction is commutative, difference is not. Product is commutative, quotient is not, composition is not commutative. I can't just switch them around and get the same answer. If they asked me to do g composed with f, then I would start with the g function, and everywhere that I see g or see an x, I would replace it with the other function, and I get a very different answer when I take g composed with f.